Hello. Today we will talk about penalty function method and augmented Lagrangian method for constraint optimization. Let us consider a very simple optimization problem. A minimum of function of one variable, even linear function, f of x, subject to very simple constraint. X is less or equal to 0. Here I draw feasible area for x. And we want to solve it with penalty function method. So we build a penalty function phi, which penalizes values of x which are out of feasible area, in this case positive x's. For example, we can take an exponent which is written here. The exponent may be a bit difficult function for optimization because it grows very fast, and even for moderate x's it may be out of computer floating point number representation, and we will look at other functions a bit later, but this is a very simple motivating example. And we build the so-called penalty aggregate, sum of objective function f of x plus penalty function. And what we do, we minimize this aggregate with respect to x, and the point of minimum we will call argmin of this expression, and we will denote it as x bar. X bar is argmin of our penalty aggregate. Let's think together where the minimum of this aggregate will occur. At the point, I claim that it will happen at the point where negative derivative of f of x will be equal to positive derivative of phi of x. Mean derivative of all penalty aggregate will be 0. And here is my point x bar. As you can see, our solution is not very accurate. What can we do to make it more accurate? We can build a family of penalty functions. For example, I can parameterize this with parameter p in this way, written here as 1 over p phi of px. And as parameter phi will grow, my function phi p will become more and more close to so-called ideal penalty function. What does it mean, ideal penalty function? It's written here. It's a function which is 0 in my feasible area, phi infinity is 0 when x is feasible, and infinity otherwise. So, our strategy is very simple. We start with some moderate value of p, we minimize we already have this parameterized family of function and also our penalty aggregate, and also minimizer xp will be an approximation of solution of our problem. So we minimize aggregate under some moderate value of p, increase gradually p, say increase it 3 times or 10 times, minimize again, and so on until we reach really large values of p, say 1 million, and then we stop the process And we can know that we got, as a result of our optimization, unconstrained optimization, is accurate enough approximation of function minimizer. The problem with this approach again is when penalty function become more and more steep, unconstrained optimization may become more and more difficult. Like I told, when we force penalty parameter to become very large, numerical optimization and constraint optimization become more difficult. In order to alleviate this difficulty, people use Augmented Lagrangian, or in other name, Penalty-Multiplier Method. What we do for this method, we introduce another parameter into penalty function, and we call it slope or multiplier, and it denoted as mu, and it controls the slope of the penalty function at the origin. You see the tangent line to the penalty function, it's just linear function mu x. As an example, one example of such penalty function, penalty multiplier function, we can just take a usual penalty function, which is built, for example, in the way that its derivative at the origin is 1, and multiply it by mu. But we will see also other ways to get such construction. Okay, how we can use it, this more sophisticated penalty function, in order to get efficient optimization? Suppose we have some at some iteration we have some parameter mu, and in our simple example of minimization, linear objective function under constraint x less or equal to 0, we minimize penalty aggregate. Again, what is our penalty aggregate? It's f p. We have one more parameter, mu. It's f of x plus phi p mu of x. Okay, so we minimize it with some parameter mu1, and get its minimum at point x1. So at this point, positive derivative of penalty is the same as negative derivative of objective, in order to have a total derivative 0. Now we do a very simple thing. We take this derivative, we take phi prime, this slope at our solution, phi p mu1 prime at the point x1, and we build the next penalty function in the way that its slope at the origin reproduces this slope which we already had. Let's try to do accurate picture. So this is our next penalty function. This is phi p mu2, and we took mu2 equal to this expression. So we built a penalty function which has this slope, which compensates our objective function in the origin, and it's rather clear that if this was x1 was argmin, I have not enough room, argmin of penalty aggregate with the first value of mu, then the second minimizer, where can I do it? Not enough room. The second minimizer, x2, is argmin of f. Here we had p mu1, p mu2 of x. In our example, we will get exactly to the accurate solution of our problem, because we see that the minimizer of f of x, subject to x less or equal to 0, f of x is decreasing function. Of course, the accurate solution is 0. Now let us generalize the present method to the case of general optimization problem with multiple variables and multiple constraints. So suppose we have to minimize the objective function f of x. X is n-dimensional vector, subject to several functional constraints gi of x less than equal to 0. Okay, in similar way like we told, we build the penalty-multiplier aggregate. We only now take penalty function not of x but of every constraint, because we want constraint to be less or equal to 0. At every iteration of penalty multiplier or augmented Lagrangian algorithm, we minimize the aggregate with respect to x and get, in this case, in this way, new iterate of x, and then we update multipliers in the way that derivative of every penalty function at the origin at the next iteration will be equal to derivative of this penalty function at our current minimizer. And also we should note that we are interested in some moderate value of penalty parameter. I remind you, penalty parameter forces the penalty to become more aggressive, more close to ideal penalty when it grows. And one can show that the iterations of penalty multiplier algorithm converge faster to the solution of constraint optimization problem, but every unconstrained optimization problem become more difficult. So we need to balance how. And the general approach is start with some moderate values of p, say for example p is equal to 1, and then increase it at every iteration 2 to 10 times, until it reaches some reasonable moderate values like 100 or 1000, and stop after this. So we increase penalty parameter only if it less than this reasonable penalty value. And the interesting thing that in this one of the reasons why it called the Augmented Lagrangian method, parameters mu over iterations converge to Lagrange multipliers of our optimization problem. More than this, if we know accurate Lagrange multipliers of our problem and substitute them from the beginning as mu, then one can show that even in one unconstrained optimization we can get accurate solution to our problem. On the other hand, if we have if we have some idea about range or approximate value of Lagrange multipliers and start with them as initial value of mu, it accelerates whole optimization process significantly. Now, regarding the concrete choice of the penalty function, like I told, the most simple is just taking exponent, but disadvantage is that exponent of several hundreds of thousands just doesn't exist in usual floating point arithmetics in standard computer. And also exponent has very higher order derivatives, and who knows Newton method, the quadratic approximation used by Newton method of this function is not very good. So numerical optimization it's not very efficient. Unconstrained optimization. Better choice is, for example, to choose a combined function which has a branch of type of quadratic function and other branch built on the base of logarithmic function, and they are connected smoothly, so the value and first and second derivative of first branch and second branch are the same at the joint point. And here is the explicit formula of such penalty function. It's very recommended, and it's rather stable and efficient. Now, for problems with equality constraints, like here, minimum f of x subject to hi of ax equal to 0, we need a double-sided penalty. The simplest one is just quadratic penalty. 1/2 t squared, 1/2 for normalization. And if we want to build penalty multiplier function, pay attention that this penalty has slope 0 at the origin. We can add another term, it's a linear term mu t, and it will provide the slope. So this is our penalty multiplier function, and the aggregate, it's like was in case with inequality constraints, objective plus some penalties of constraints. But in this special case, it has a very nice look. The objective plus mu. Mu is a vector of slopes of those penalty functions. Mu transpose h of x, which one can recognize standard Lagrangian here. And plus usual regular penalty for squared for second norm of x, which penalize the difference between h and 0, and that's why the name Augmented Lagrangian method. So we have Lagrangian, standard Lagrangian, and the quadratic penalty term as an addition. Now, just one word about update of multipliers in this case of equality constraint. So we see that penalty multiplier function has this special form, and its derivative is very simple. It's just mu plus pt, and like we remember, update of multipliers. The new multiplier at new iteration is just derivative of penalty multiplier function with respect to corresponding constraints. And when we substitute, we get a very simple formula. is just our previous multipliers plus penalty multiplied by value of constraint. And this is a very simple and attractive algorithm, and it is very popular recently in many application areas.